right, part 3. Welcome back. Diving right in. We left off right here on the last video. Go back and watch video 2 for sure. But it was asking us, we just found number 5. We found the probability of L given R was 0.17 and the probability of R given L was 0.61. So we're going to need that for number 7. Number 7, are R and L independent? Why or why not? The way that you test independence is you do one of these two things. You could do this. You could find the probability of R happening and compare that to the probability of R given L. You could compare those two. Or you could do the other way, find the probability of L and compare that to the probability of L given R. Because the test for independence is simple. If those two probabilities are equal, then they are independent. If those two probabilities are not equal, then they are not independent. Here's why. The probability of R happening. What was it again? We already found, see, that's the good news. We already found all those. So the probability of R happening was 0.78. So the probability of R happening is 0.78. The probability of R given L happening is 0.61. So when you look at these numbers, does it look like L had an effect on the probability of R? Sure, that's a drastic difference. Those are not equal. L is affecting R in some way. So we don't even need to do this other one, but you can just see from right there that these are not independent. Go back and watch that again. That's how you test for independence. You end up using a given and just an original probability. All right, next problem. We got to do one where you're given a chart like this. Create 2 pie charts. Nah, we know how to do that on Excel, right? Pie charts, click, highlight, go up top, click pie chart, copy, paste, do one for grades, one for popularity, one for sports, broken down by gender. Shout out to Excel and R. We're coming back for you soon. Okay, what is the probability? I'm looking at number 2 now. What is the probability that a person selected randomly from this survey is female? Well, we know probability is simple division. It's the number that you're looking for divided by the total. So in this case, female. How many females are there in this survey? There were 251. So 251. How many total people were surveyed? 478. So there's my answer. Get the calculator going. Approximately 53% were female. Let's keep rolling. What's the probability that a randomly selected person's goal is to excel at sports? Well, let's look at our chart. The goals of excelling at sports. 90 total people chose that. So that's going to be our number on top, 90, out of total on the list, 478. So 90 out of 478 says that about 19% of people have a goal of excelling in sports. Number 4, what is the likelihood that a randomly selected person is a female who also wants to excel at sports? Well, that's it's going to be a smaller probability. So we can go up here and just circle the females who want to excel at sports. That's 30 out of 478. What is the likelihood that a randomly selected person is a female who wants to excel in sports? 30 out of 478. Stay with me because it's about to become slightly more complicated. I know so far this is simple division. We don't have to overthink some of these. That is 6%. Yeah, okay. Let's keep rolling. Number 5. What is the likelihood that a randomly selected person is a sports person who is also a female? Okay. Let's make sure we set this up right. What is the likelihood that a randomly selected person is a sports person who is also female. So this wording is tricky, but let's do exactly what it's finding. The probability that someone is a sports person given that they are female. Let's see if we can find that. That's rule number 8. Rule number 8 tells us on our sheet that we want to find the probability that someone is a sports person and they're a female. We'll be able to just use our chart for that, divided by the probability that they are female. So we are looking for the probability that someone is a sports person and a female. How many are those? How many of those do we have? Sports person and female. That's 30. We just had found that on the previous question. So 30 over probability of a female. So female will just be 251, which equals 0.12. All right, number 6. What is the probability that a randomly selected person is a male? And, like, I know it doesn't say and, but I'm assuming it's like, okay, a male who wants to get good grades, so we need to find the probability that they want to be a male and they want to give good grades. So what this problem is asking is this: male and get good grades, which would be, we can just call that a G. So an and problem, we can just look at the chart. Male and good grades, that's this number. Sometimes the chart makes it a lot easier. It's 117 over 478, right? What's the probability that we select a male who wants good grades? That's 117 of them over the total 478. And that probability .24. Number 8 is wanting to get good grades independent of gender. The way we test independence is we find something like this. What's the probability that you're a male? And then we're testing grades and gender, so we need to compare that to the probability of being male given you make good grades. So what's the probability of being a male? Have we found that already? No. So let's just do 227 divided by 478. 227 divided by 478. Find the probability of being male. 0.47. That's 0.47. You need to compare that with the probability of male given that you have good grades. So this is a little trickier. We need to just go straight. So given you have good grades, that means we're just looking at this column. What is the probability that you are male given you have good grades? That's 117 over 247. It's a different total. Probability that I'm male given that I have good grades. What do we say? 227. What is that decimal? It's 0.52. So I would say that getting good grades is not independent of gender. I mean, that's a 5% difference. I think that's big enough to say that those are not independent. Is wanting to be popular independent of gender? Is wanting to be good at sports independent of gender? See, we're doing some cool things. You can do this when you are making contingency tables. You can use this to as a way to enhance your contingency tables. Drop some probabilities in. So is wanting to be popular independent of gender? So we need to find the probability of being a male again. Let's just use that, which is 0.47. You need to compare that to the probability of being a male given that you want to be popular. Let's do that one real quick. The probability of being a male given you want to be popular. So here is the given you're popular. So that's the condition we're zooming in on. What's the probability that you want to be a male given you want to be popular? So 50 over 141. 0.35. Ooh. So that shows that those are not independent. Looks like men want to be less likely to want to be popular than women. Last one is wanting to be good at sports independent of gender. Since we're testing all these to gender, we can just use probability of being a male again, 0.47. Compare that to the probability of being a male given you want to be good at sports. I have a feeling this one's maybe going to tend towards the men. I could be wrong. We're just looking at the data. So what are we doing? Probability that you're a male given you want to pursue sports. So we're living in this sports column here. Probability that you want to be male, yeah, you can already see it. It's 60 over 90, so it's going to be bigger. So it's 60 over 90, which is 2/3, right? 0.66. So this shows, once again, not independent. So there you have it on that sheet. We just finished this conditional probability sheet. I'm going to jump over to one last thing. I'm going to pause the video here. All right, last few minutes of these video series. Hopefully this helps you. It's another chance for us to practice our Venn diagram. It says a group of potential vacationers was asked about their favorite kind of vacation destination. And it looks like 60% say mountains, 80% say oceans, 55% say both. So we'll put the 55 in there. So if 55 says both and 60% said mountains, that means that there's only 5% that were mountains only. Because remember, 55% said both, so like 55% of that 60, almost all of it, they like both. But for oceans, there were more people, 80 minus 0.55, which is 0.25. So if this is the mountains, this is the oceans only, mountains only, this is the both category. So that adds up to be 70, 85, so there must be 15 that don't like either. They don't like mountains or oceans, so they definitely don't like both. Using that Venn diagram and just all of our probability rules, let's solve some of these real quick. What's the probability of someone liking mountains? Well, that's right up there in our sheet. It doesn't say mountains only, it just says mountains, so 0.6. What's the probability that somebody doesn't like mountains? Well, that's 1 minus 0.6, using our complement rule. What's the probability that someone likes mountains and oceans? That's the middle 55. What is the probability that somebody likes mountains and then they don't like oceans? Okay, so now we're cranking it up. Might only be able to finish number 4 and number 5 here. So what is the probability that somebody likes mountains and does not like oceans? So that sounds to me like somebody who likes mountains only. So theoretically we can solve it just by looking at our chart. It equals 0.05. Here's how we do the math with that. The probability, this is also could be rule number 7 if we wanted to. So the probability that someone likes mountains, that's the first thing, multiplied by the probability that someone does not like oceans given that they like mountains, which is kind of what the question is asking. Probability that somebody likes mountains is 0.6 multiplied by, moment of truth, probability that somebody doesn't like oceans given they like mountains is going to be an AND problem. What's the probability that somebody doesn't like oceans but they like mountains? Well, that's 0.05. So that's going to be right here. Divided by probability that somebody likes mountains, which is 0.6. So it's real quick before we run out of time, 0.6 times 0.05. I ran out of time. Just do this multiplication.